First of all, I'd like to thank the organizers for giving me an opportunity here. And this is an interesting session, started with photovoltaic, especially CIGS thin film, which is advanced cutting edge technologies nowadays. And very interesting topic by Dr. Ayodhya N. I am going to change the gear to more practical, immediate work that we are doing. It's on solar thermal energy. I'm going to talk on technology issues and future. I'm going to tell something about the solar radiation, my comments. Then I'll talk to the industrial process heat. So solar energy can also be used for industrial process heat. In fact, that is a more easier and direct way of using solar energy, and there is a lot of potential. Lot of things are already happening in India, and we are almost on the forefront in the world. We are also working on solar thermal power, and there are issues in it, and there are many advantages in it also. So I'll cover my topic on this. To begin with, on radiation, as Dr. Tiwari has already told about the solar radiation being abundant, one of the thing in India is we have good radiation. However, compared to last 30 years, the radiation has gone down mainly because of the pollution. So the one that is received on earth in India has gone down a lot by about 20 to 30%. That's what we can see from the data of 1980 and data now 2010. There is a significant difference, basically because of the brown cloud that we have on India and China. So whenever you design a solar system, it should be based on the ground data rather than on a web data or typically satellite data. So that is one thing I would like to highlight. Okay, let's begin from this. We know that there are solar water heaters. Solar water heaters are widely used. They are used and there are evacuated tube collectors. Both of them go only up to 60 to 80 degrees Celsius. They are widely available. Evacuated tubes are available from China. About 80% of the market is from that. You are aware of this. They are used for water heating, cooking and other things. However, can this be used for industrial process heat, which has typical requirement of about 80 to 100 degrees Celsius plus, minimum 100 degrees Celsius. It goes up to 200, even 300 degrees Celsius. So can we use solar energy for that? Is it economic? So these are the various industries with different materials, either air or steam or water. They use this energy as heat. So there is a boiler or air heater or water heaters. So is it possible to use solar energy in this question, in this situation? That is a question. Also, there is a lot of hospitality sector. There is a lot of energy consumption in laundry, cooking, cleaning. These are the normal day-to-day activities immediate to us. Can solar energy be used for it? And these are the typical temperatures that are required. So our water heaters and evacuated tubes are typically not useful for these applications. Third thing is comfort cooling. Typically we experience that when there is more sun we require more cooling. So this is a good application of solar energy. So this can be done by vapor absorption system, where heating a generator is a sense refrigerant generator can cool the system, and if the generator is at higher and higher temperature, it's better. The COP kind of efficiency is better at higher temperature of generator. So can this be done? Just another example is cooking in household or community cooking also requires the energy at this temperature. So can we use this energy, because most of this application we use oil which is imported. 80% of the oil is imported today. These are mainly in medium industrial units where land is available to put solar panels, solar systems. Typically we have to aim at about 10 bar, which is 180 degrees Celsius. We have a lot of skill, so concentrators can be used. So the main thing is, if I have to go to 180 degrees Celsius, flat plates are not okay. We have to concentrate the energy by some reflector, lens or something like that and go to high temperature. So these are a bit complicated systems, tracking is involved, but they can be fabricated because we have a lot of skills at lower cost compared to the world. So about 20 years back, we have started, many people started, 2-3 groups started in it, and we have started working on the concentrator. So, I will just explain what is this concentrator for the students and other participants. Concentrator is basically a parabola. Parabola is at the heart of the system. A parabolic reflector has a property that all parallel rays parallel to its axis concentrated at its focus. So, this property can be used in 2-3 different ways. This parabola can be used and rotated to get a paraboloid structure with a point focus, or it can be extruded to make a parabolic trough with a line focus. Further, this can be broken into pieces, brought on a ground on a flat surface. This becomes a LFR, linear Fresnel reflector, or it can be, or the paraboloid can be broken into pieces, brought on ground, that becomes a heliostat or Fresnel concentrator. So, these are the 4 basic types of concentrators which are used. They are used for parabola as dish system with Stirling engine at its focus, or solar tower system with a central tower receiver going to high temperature, or parabolic trough which are very common with a line focus system, or linear Fresnel reflector. Each one has different scales, different costing, different limitations also. All this system, when we compare, there is a basic equation that efficiency is given in terms of optical efficiency into the solar radiation received minus losses. So, we work on this equation. In fact, much more detailed form of this equation we use, and various components are identified, so that we can identify how our system can be improved. So, this is a basic form of equation, efficiency split into optical efficiency and loss coefficient. The one important thing about this equation is that, well, you can see the first term can be constant if I have optical efficiency as constant, but the second term is sensitive to temperature. So, if I operate the system at higher and higher temperature, the losses are more and more and the efficiency goes down. So, we have to handle this when we need to operate at higher temperatures. This equation put into a graphical form shows that as the temperature increases, efficiency drops. And as Dr. Tiwari has rightly said, there is no one single answer. For different applications, we have different ways, different devices, different concentrators. For different temperatures, we will have different concentrators. So, for example, if there is a swimming pool heating, I won't use concentrator. But suppose I want furnace melting of iron, then I cannot use flat plate. So, there has to be a choice of concentrator depending on the temperature application and some other considerations also. So, this is the gamut of solar concentrators. In India, we do manufacture concentrators. There are 4-5 leading manufacturers. This is a system put in NICE, National Institute of Solar Energy, which is at Delhi, south of Delhi, Gurgaon, near Gurgaon. So, this is installed for 100 kilowatt of cooling. It is 26 TR system, parabolic trough, Indian made, with tube, without evacuated tube, and oil is circulated, and lithium bromide system is used to cool the space inside the office of NICE. This is a Scheffler cooker. You must have been aware of this name. Scheffler cooker is a part of a paraboloid, and it has an interesting property that its focus is fixed on ground. So, we can have a focus inside kitchen and we can cook the solar system. In a large scale, we can have many of them generating steam, and that steam can be used for cooking cooking in large scale through steam handling devices. This is linear Fresnel reflector installed at a company in Coimbatore, about 800 meter square, in which mirrors are installed on ground. They are differentially inclined and tracked around that circular trackers, and you can see at the top there is a receiver here. So these are the two receivers on which this mirrors reflect all the energy. So we can pass water through it and go up to the steam. We can go to 250 bar. We can go higher with this. This is a spherical bowl. This is at nearby Pondicherry. This is in Auroville near Pondicherry. This is a 120 meter square, 15-meter diameter spherical bowl with a receiver which is, so the lighted part, this part is actually a receiver. It's a coil through which water is circulated and 140 degrees Celsius steam is generated through this system. Here the bowl, the reflector is fixed and the receiver is tracking. So there are various kinds of it. Then we have 2-3 different designs from different companies of reflector, a 90 meter square reflector, there is a 25 meter square reflector which has a paraboloid shape. One of the interesting design is the Arun solar system which we had researched on and commercialized. The structure need not be paraboloid in this case. So structure is flat and the mirrors are mutually inclined to get the parabolic effect, so that the quality control is very easy, cost can come down. So this is being used as solar boiler up to 10 bar or even higher temperature in industry. This is again a picture of the same Arun system, 160 meter square at NTPC Netra, Greater Noida, where it is used for cooling. It's about 50 TR cooling is there, 200 kilowatt cooling. This is at Akshardham in Delhi, 100 meter square system. So where all these reflectors mounted on a flat surface concentrate the sun rays at the focus, at a receiver at the focus where it is boiling into steam. So it's a boiler, it's a solar boiler. We go through the IBR process and other things. So this is the application of solar energy for industrial processes for boilers, and we have come a long way. We have been doing it. Some of the pitfalls is we have to select a concentrator for the application. As I said, depending on the temperature, what is the concentrator to be used has to be selected. Again, depending on the load characteristic, is the load during daytime or during night time? Accordingly, the system has to be selected. Should there be a storage or not? We also need to have solar radiation data. If the radiation is very low, then it's not economic to put the concentrator to generate heat. Also, what is the fuel saved? If the fuel saved is costly, if it's oil, if it's gas, it's a costly fuel. So saving it is more economic. However, if I am using it for coal, then there is a problem. Then economics is not that good. So I have to look at the fuel being used in the industry. But at present, about 30 to 35 industries in India are using such system. I will go ahead. One of the challenge here is the integration. The solar energy has its own whims and fancies. It is available only during daytime and there are cloudy hours. But industry cannot agree to that. Industry works 24 hours or maybe sometimes early in the morning, or only small hours it will require the heat. So we have to optimize the integration. How much storage to be provided, how much collector area to be provided. This needs to be done, and this graph shows that a allowed combination of collector area and the storage is studied by optimization methods. One more thing about this application is cogeneration. Here in Ramnathpuram, Tamil Nadu, south of Tamil Nadu, a Coimbatore company, KGDS, has installed this system which generates heat, steam at 40 bar and generates power, and then the spent steam is used for desalination. So in the Ramnathpuram area where there is a drought, the sea water is converted to potable water by this system, and 24-hour system is installed there. So this is also an interesting application of solar thermal energy at high temperatures with concentrators. With this background in India, we have a lot of work done by various industries, various groups in concentrator. We are now looking forward to the solar power systems. The issues are how is the ground for performance? Can we assure the ground performance? What is the cost? At what cost? Of course, for oil or gas replacement, these systems are economic, 2 or 3 years payback, but all depends on the site data. One of the major challenge today is reliability of these devices for long term, 10 years, because these are moving systems, complicated systems. So, a professional engineering needs to be done. So, this is the problem about the industrial process heat, and with this experience, we are now going to solar thermal power. You will ask me what is the relevance of solar thermal power. So, one of the issue is solar thermal power is costlier. Okay, compared to solar PV, solar thermal is certainly costlier. It's about 14 to 25 crores per megawatt is the installation cost compared to solar PV of 6 to 9 crores per megawatt. So, it's about 2.5 times the solar PV cost. However, the capacity factor is about 1.5 times. So, solar PV works for 1200 to 1500 hours a year, but this will work for up to 2000, 2500 hours per year. So, that, but it doesn't really make up that much. So, what is the relevance of it? So, before that I will explain you what is this solar thermal power. Typically a concentrator, on the left we have shown this concentrator, oil is heated and the hot oil is circulated through superheater, boiler and preheater, by which steam the turbine is generated. So, it is a normal thermal power plant, only thing is steam is generated by solar energy at that temperature, maybe about 400 degrees Celsius or something. And then of course, there are other power systems. This can also, in the night the oil is heated by hot oil, it can be heated by hot oil. So, we get the power throughout day and night. Other possibilities with the heliostat, as I said, central tower systems, they can concentrate their solar rays onto a receiver and then we can heat molten salt to very high temperature of 565 or 600 degrees Celsius and this can be stored. So, this is one possibility that solar thermal technology opens up, that we can store thermal energy and generate even at the night. So, the problem of peaking and problem of continuous power supply as a base load can be addressed by solar energy. That is one of the major things. One of the issue is, as we looked at the graph previously, as temperature increases, efficiency of the solar plants decreases, but as temperature increases, turbine efficiency increases. So, we have to decide at which test should we operate at lower temperature. If I operate at lower temperature, I will get more energy, but the turbine efficiency will be lower. If I operate at high temperature of say 500 degrees Celsius, turbine efficiencies are good, but then solar efficiencies are lower. So, we have to strike a balance and optimize the system. So, this is one of the design issue in solar thermal power plants. We have 3-4 power plants in India. This is Acme Solar at Bikaner, 2.5 megawatt operating at 1.5 megawatt. This is heliostat bed. You can see the mirrors distributed all over the ground and a central tower on which all the mirrors reflect the energy. This is parabolic trough, Godavari Green Energy at Nok in Rajasthan. This is Reliance Ariva system at Dursar, 125 megawatt. This is a LFR system. So, we have all 3 types of system, and one of the system that we at from IIT has designed and installed at NICE in Delhi is a combination of technologies. That is, on the right you can see the LFR system, on the left you can see the parabolic trough system. LFR systems go to lower temperature of 250 degrees Celsius, but they are more economic. So, it generates steam by that, and by parabolic trough heat oil to 400 degrees Celsius, superheat it, so that you can get better efficiency from the turbine. So, this combination is unique. Nowhere in the world people have done this, but we are running plant on this system. And there is a test center also on the right. You can see a building, small building, which is a test center. This is a data that we actually generated the power on that 27th May 2014, and you can see that it has gone up to 600 kilowatt for some time, 2-3 hours. This is another interesting system. We are using 64 meter square Scheffler system, which is now installed and now turbine is being rolled with the ingot of 3-ton iron at its focus through which pipes are circulated, so that we can heat the iron block during the day, and in the night we circulate water and get steam. So this is a 1 megawatt 24-hour plant that has been installed by Brahmakumari Ashram at Abu in Rajasthan, and it is almost commissioned now. Turbine has been recently rolled, so they will go online soon. So as I was saying, issues are like this. It is costlier. So our energy target is energy cost target is up to 6 to 7 rupees per kilowatt hour. If solar thermal can meet that, then it makes sense. However, one of the advantage of solar thermal is dispatchable power, in the sense that it can act as base load. It can provide from 8 o'clock, 6 o'clock to 8 o'clock or 9 o'clock in the night. That is an advantage of solar power. This solar PV or wind cannot do unless there is a battery or compressed storage, which are inefficient by itself. So 24/7 supply is possible, and many people are now working on it. For this, we have to work on heliostat controls. We are working on cavity receivers of new types. Storage material is molten salt, so we have to learn to handle it. There is LFR based PCM storage is to be used. Again, salt is melted and solidifies, and the heat required for it is stored and recovered. Integration of different solar fields, optimization of the field, these are the various technical challenges that we need to address, and people are trying to do that. Cost is another issue. So while doing this, the cost should not shoot up, but one of the thing is, most of the parts of the technologies, almost all of the parts of the technologies are available in India, and we can 100% indigenize. So we are not dependent on any other country. For example, silicon based PV panels are at present 100% imported from China. So there is a lot of activity, but it is not encouraging the local economic activity. So this is one of the problem of silicon based solar. So this system can also address that, provided the last point is if we can develop this engineering and fabrication capacity here. So there are various groups which are working on it. IISc Bangalore through its Shireesh project, it's a solar energy research in India and US system. Heliostat design and farm layout. So heliostat, what should be the size of heliostat, how does it track? These are the issues that they are trying to handle. Supercritical CO2, supercritical carbon dioxide is an interesting variation rather than the steam system. Instead of water converted to steam, you can have 300 bar pressurized carbon dioxide heated to 700 degrees Celsius, and that can be used as a material for transfer of heat and extraction of power from the turbine. So this is what IISc Bangalore is working on it. This can have very high efficiencies of 50% plus. So this is an advantage of it, or maybe 60%. Molten salt loop, having a molten salt loop, what are the materials, how to handle it, what are the pumps and other equipment. So these are the issues that IISc is working. IIT Jodhpur is working on dust level, dust deposition, degradation of the receiver and reflector, tracking of heliostat. BARC is working on another concept called beam down heliostats. So all the heliostats concentrated on a mirror at say about 50-meter high tower, and that mirror is shaped such that all the energy is again brought down on the ground, so that the boiler and all system storage can be at ground. You don't have to pump anything. So natural circulation molten salt receiver, they are working on it. In IIT Bombay, we are working on high temperature cavity receiver with coil tube, which is not typically used. We are also working on PCM storage in this Shireesh project. We are also working with NTPC because they are the power generators. So if some of their heat is replaced by sun, then we can save a lot of coal emissions and other things. So on heliostat tracking, Fresnel optics especially, because all over the world the receiver heliostat is actually curved. Instead of that, can we have Fresnel optics so that flat structures are used? molten salt loop with plated receiver. This is a new concept that we are working on it. Thermocline storage, in the sense that instead of 2 tanks for storage, we can have 1 tank and a layers of heat in it. So that is one possibility, hybridization of 2 systems as well as phase change material storage. So these are the issues that we are working on it. In India, we see that 24/7 power can be available through solar, which can have a dent on the power scenario by renewable. Otherwise, that is considered as a problem with renewable, that it is not available at demand. Whenever sun is available, whenever wind is available, only then power is available. Instead of that, through storage, we can generate power whenever we want. If there is peak, we can supply to that. That is what is the aim of all of us. I will take 5 minutes to explain this concept of storage. Typically, what happens is this graphs show the energy developed by solar system throughout the day. On the x-axis is time of the day. So by 8 o'clock, 9 o'clock, sun has risen and we generate good power, and then sun sets at about 6 or something. So 5 to 6. So this is the energy generator. However, when I feed it to turbine, say for example, for a given field 7 megawatt turbine can operate, minimum rating is 30 to 25%. So this is the minimum steam rate that it can absorb, and this is the maximum steam rate, blue one, that it can absorb. So energy above it is wasted and energy below it is also wasted. So morning up to 10 o'clock or 9 o'clock energy is wasted, and after 5 o'clock energy is wasted. Not only that, the noon energy is also wasted because this cannot be absorbed. Instead of that, if I have storage, then I can have a 2.5 megawatt system running continuously. Say for example, this 2.5 megawatt has minimum steam flow rate at this level, white dotted line. So I can start early at 8 o'clock and end at 6 o'clock, and anything above it can be stored and fed in the night. So that is how we can optimize. Typically the numbers show that if I optimize without storage for a given field, I get about 10% variation in the generation if I optimize it. So instead of 7, if I put 3 megawatt, it will generate less. Instead of that, I put 10 megawatt, it will generate less. So there is an optimum value for 7 megawatt for this field. But suppose I run it with storage, I can generate 10% more. So instead of 15,000 megawatt hours per year, I can generate 16,000 megawatt per year from a 3 megawatt plant. So this is what the storage plays a role. So mastering handling of storage, controls of the system, this is what we are all working on. In this, of course, we are also globally partnering various agencies, mainly for testing lab, reflector testing, life of reflector, degradation of it, improvements on critical components, especially reflector, is what we are collaborating through NTPC, through ISC or various projects. And one of the major issue that we need to face is that awareness. In a way, that's why I am here, that see, this can be done. Solar energy can go up to 100 degrees Celsius, 200 degrees Celsius. We are now thinking of 565 degrees Celsius. So solar energy can generate this, and we can use it effectively even during in the industry. It's not only for power. A normal industry can use solar energy and save a lot of oil emission now. It's nothing in future. So this is what we are working on. If the mass comes in, we work on various issues together, and we can accelerate the development very fast. So that is what I have to say. Thank you. Thanks for patient listening.